All right, so in this video, we're going to continue with our analysis of time series, and we're going to reload our data set that we were looking at in the last video, the seatbelts data set. And we're also going to extract one of the columns of data, which is the number of people killed overall. Which is just the first column of variables. And if we just look at the data set, again, it's just a vector that the vector that's displayed as a table because we have data from each month across several years. And what we're going to do is we're going to replot the graph that we looked at in the last video just to sort of orient ourselves. Now, what we're going to try to do in this video is we're going to look at the decomposition function to try to separate out seasonal components from any trend components, from any noise components, and so forth. So we're going to use the decompose function. So I'm going to call it something, and I'm going to decompose this one time series variable. Now, by saving it as something, that means that I can extract various pieces of it to use at a later time. So if I run that, and then I can plot the results. And so the plotted results, and again, you can use the zoom feature in the plots menu to expand the window and look at it in more detail. But you can see that on top, we have the observed data, so that's the original time series data. The second piece is the trend as we go down. This kind of strikes me as a random walk. Seasonal component, so this is trying to extract a common pattern that things tend to follow. We can see there's a low period and then a high period that these, my guess, if I had to guess, would probably be related to weather. So maybe when the weather is particularly bad, you'll get more accidents. And when the weather is better in the summer, then maybe you'll get fewer accidents. And then the random part, that is sort of the error after subtracting out the trend and the seasonal component, this is what's left. And this is the error that you want to look noisy and stationary and random. Now, decompose will not work on every possible graph that you have, every possible time series data. You have to be able to have a certain amount of data, and you have to be able to have a recognizable trend. And some data sets, even though they appear to us to look like there's a trend, they actually can't be decomposed very easily by the decompose function. So we reload our sunspots data, and then we can look at the data. Again, it is separated out into, there's a lot of years here, but it's separated out into various months. And these appear to be the average count of sunspots across that month. They're not like the maximum or anything like that, because you can see that there are decimals, and so they have to be at least some sort of an average rather than just a count. And then we can plot the sunspots data. And this is the plot that we saw last time. Again, there is clearly some kind of a cycle going on. And in fact, we know from scientific analysis, there is an 11-year sunspot cycle, but some of these cycles have more sunspots, some of them have fewer sunspots. And it turns out that the decompose function is going to have problems decomposing this data set. because of that fluctuation that we see. So you see what happens. And again, you can zoom in order to um, graph the results. What you can see, okay, you have this random component at the bottom, which looks quite noisy, which is great. Our original data set up top. The trend seems to just follow basically this 11-year cycle, sort of, washing out, um, smoothing out some of the pieces of it, but basically it's seeing these 11-year trends, and the seasonal component is just noise. This doesn't look like much of a seasonal component at all. And so, again, the decompose function works really well when there are sort of clear cycles that happen repeatedly, particularly over like a 1-year cycle or something like that. But this, or a weekly cycle if you have daily data, but this clearly does not seem to be very friendly to the decompose function, given the nature of this particular data. So again, it's just the way that the data set is. This decompose function works really well for certain kinds of data, and then certain other kinds of data we have to go to other kinds of analyses. Now we can, for these decompose analyses, as long as they don't give us an error, we can look at some summary of the results. So they'll give us the length of our X variable, the length of the seasonal, the length of the trend, and so forth. They gave us some general information about the data set, not like summary statistics or anything. We can extract various components. So we could extract, for instance, just the trend component. And we could plot individual components that we want to look at more specifically. So, for instance, we could just plot the trend. And we could likewise plot the seasonal. Again, it's really nasty and ugly looking. This is not what I would call a seasonal pattern at all. And we can also separately plot the random component. And again, if we can plot it, then we can do further analyses on these components. We could do analyses such as plotting the random component as a histogram or something like that, that we could also then use to assess the normality of the errors and things like that that we talked about in the last video. We can also try to adjust the data set by subtracting out things like the trend component or the seasonal component to see if we can do further analysis on it. So for instance, the adjusted sun spot data set, we can take the sunspots and then we can subtract off the decomposed trend value. And then we can plot the results. We could also try subtracting out the seasonal component, such as it is. That's because I did this wrong. Sun decomp. Try again. There we go. Again, the seasonal component was just very noisy, so this looks basically like very similar to the original data set. Now, if we were to do something very similar for the killed data set, we would actually be able to get a little bit more information about the killed data set because that decomposition worked a little bit better. So we can replace this with K decomp. And if we replace this with a graph of the K decomp, the decomposition of that killed variable, again, we can extract the trend, which looks, again, like a random walk. The seasonal component, again, looks very regular. And the random, and then likewise, we could actually calculate adjusted data sets by subtracting out the trend. So this would basically be the seasonal component plus the noise. And if we subtract out the seasonal, then we would have just the noise plus the trend. So we can not only plot the individual components, but we can remove them from the data set one at a time to do further analysis on it. Now, we could try to do a LOESS model to try to model the trend, particularly in our sunspot data or in our number of people killed data set. So let's see if that will do any better job. So STL is the LOESS model for our time series. Sunspots, comma, S window, the seasonal window, periodic. And we're going to then plot and again, our seasonal component is in a slightly different position, but the LOESS model did not actually do much better job in terms of extracting the seasonal trend. That 11-year sunspot cycle just doesn't seem to be recognizable to some of these functions. If we did the same thing with the killed data set, we will have a little bit more success. We should get something that looks similar to the other decomposition. And again, the trend is in a slightly different spot. It's lower, the seasonal is above it, but this behavior that we see, again, still looks like a random walk. The remainder, the error, the random part is plotted with bars instead of as like a line graph. But the seasonal trend looks very similar to the one that we got from the other decomposition function. Now, one of the differences with time series analysis that is different from other kinds of cross-sectional data analysis is that longitudinal data like this can be correlated with other values in the data set. So the correlation, the errors are not independent, they're correlated with each other. So what we can do is one of the reasons why we were looking at the differences in the previous video. We can plot graphs like ACF graphs and PACF graphs. These are autocorrelation graphs. The ACF is the full autocorrelation function, and the PACF is a partial autocorrelation function that tries to take more of the, so the autocorrelation function just looks at lags, one observation against another observation, and then tries to look at how they're correlated. But the PACF tries to take into account correlation with intervening variables. So if there is a correlation between an observation and a previous observation, the ACF will not take that into account when it figures out the correlation between an observation and two observations back. But the PACF graph will try to take those consecutive correlations into account. And so remove those lag 1 correlations to analyze the lag 2, and analyze and take those lag 1 and 2 into account before it analyzes lag 3, and so forth. So we're going to look at the ACF. We're going to use the data set that is going to behave a little bit better. This one also has a little bit less data in it, and so that'll be easier to interpret. And so here we have an autocorrelation, and what we see is that the autocorrelation graph, again, these bars are representing the level of correlation. When there is no lag, in other words, you're correlating a value with itself, you get 1 correlation, because it's just like correlating MPG with MPG. But then as you go back in time, you can see that not only is there a 1-year cycle, there's an autocorrelation out here, there is an autocorrelation with the previous month's variables as well. That's about 0.6, that's fairly high. As long as the bar is above the blue line, then that is an indication that is statistically significant. If it falls inside the blue lines, then it is statistically insignificant. And of course, the ones that are below the line are negative correlations. If we look at the PAC graph for the same data set, then again, the 0 correlation is correlating with itself. Sometimes it's not even plotted on this graph, but we see that with 1 month back, there is a very strong correlation that is still around 0.6. And we can see that as you go out to 1 year out, you also have high correlations, that seasonal component. And so this gives you information that you can use in order to build your ARIMA models that we will talk about, not in this one, but in the next video, in the next tutorial. Now, the ACF will give you information about how many terms you need to include for a moving average, and the PACF will give you how many terms you need to include for the autocorrelation component, autoregression component. Now, if we were to do the same analysis on the sunspots data, the number of lags here is actually not doing enough, not going out far enough to actually see the 11-year cycle. And we see that all of these components have some kind of correlation with the previous values for quite some time. And sunspots are created by magnetic activity on the sun. And since it's a very long cycle, you can imagine that, yes, indeed, there would be a strong relationship. It doesn't just like turn on and turn off. The sun is a big place, and the magnetic field around the sun does not change dramatically like that. If we do the PACF on the sunspots, then we see that when you account for those longer term trends, then you actually get fewer terms that are statistically significant. Only 3 or 4 cycles, 3 or 4 months before, when you've accounted for those other correlations, that they kind of fall off. The autocorrelation with one time cycle out, 1 month out, is extremely strong. And when you take that out of the data set, for all of these other correlations, they drop off very, very rapidly relative to not accounting for that very strong month-to-month correlation.